Unit 5, Part 1, Writing Equations and Graphs of Exponential and Logarithmic Functions. Well, if you notice, these boxes should look very familiar to you because these are the same functions that we've used for, or the same traits that we've used for all the different types of parent functions. You have the A out front is your vertical stretch or compression. You have the B inside with the X is the horizontal stretch or compression. And you have the move left or right is the C divided by B, and then the up and down is the D at the end. So all those traits are the same as what we've already seen. The only thing new is we're also going to talk about whether it's exponential growth or decay. And that's just if the number being raised to a power is bigger than 1, it's exponential growth, which means the function's increasing. If the number being raised to a power is between 0 and 1, it's exponential decay. We don't worry about the negatives because that's the reflection, and we still talk about growth in terms of is that B value bigger than 1 or not. So to refresh your memory, let's just talk about what a natural log graph looks like. Well, a natural log graph had a vertical asymptote at 0 and then went through the point 1, 0 and grew slowly but grew forever. So the domain was greater than 0. The range was all real numbers. Now that was for a log graph. And it doesn't matter which parent function of logs, it's any type of log e to the x, 10 to the x, 2 to the x, any log, that's the basic shape. An exponential growth function is the inverse of that graph, has a domain of all real numbers and the range is greater than 0. Exponential decay would be going like this, where it still has a horizontal asymptote. They both have horizontal asymptotes, but still domains all real numbers, the range is still greater than 0. So that's just a quick reminder of what happened. So let's go select the blue for a second. And for this parent function, that's a log base 10. That's the standard. It goes to the point 0 or 1, 0, and then the point when you log base 10, if x is 10 and y is what goes to point 1, 10. Sorry, I was saying that backwards. So this log graph we know moves right 1 and down 2. So right 1 down 2. Well, the right 1 means that's where our vertical asymptote is now. So right 1 is now, instead of a vertical asymptote at 0, we have a vertical asymptote there. Down 2, well, normally we had this point 1, 0. Well, it's going to go right 1 and down 2. So we're going to go right 1, down 2. There's where it would touch the x-axis. And so now this graph, as a normal log graph, would follow that vertical asymptote and then goes up and out that way. So the domain is anything after 1. So 1 to infinity, but not a bracket. It doesn't actually touch it. The range, well, it goes down forever and up forever. The range is still all real numbers. It is increasing the entire time, so only from 1 to infinity. It's never decreasing, so NA. It does have a vertical asymptote. We said at y, at x equals 1. Is it 1 to 1? Yes. A vertical and horizontal line will only hit it once. As x goes to the left forever, the function does not exist. As x goes to the right forever, the function goes up forever, so to infinity. As x goes to 1 from the left, well, there's nothing from the left. If you look over here, there's nothing over here, so that does not exist. And let me erase that scribble because that shouldn't even be there, just showing you that. As we go to 1 from the right, we're going down to negative infinity. And there is our first one. Now, number 2 is an exponential function. That's like this blue. If it's 3 to the x, that's bigger than 1. So like that's a blue exponential growth function. This one moves left 2 and up 1. Well, this had a horizontal asymptote at 0 originally. So we're going to go up 1. So up 1 means here is our horizontal asymptote. So a horizontal asymptote at y equals 1. Then normally we would have had the point 0, 1. All exponential functions go through that point. Well, this one moves left 2. So if we go 0, 1, up 1 and left 2, I think that's right in here, and then we draw exponential growth. The domain is still all real numbers. It goes left forever and right forever and everything in between. The range is only greater than 1, so 1 to infinity with the parentheses on the 1. There is no x-intercept on this because it doesn't touch the x-axis. It does have a y-intercept. To find that value, I'm going to make x 0. Well, if I plug in 0, f of 0, that's hard to read. F of 0 is 3 to the 0 plus 2 plus 1 power. So that's 3 squared, which is 9, plus 1. We get a y value of 10. That's our y-intercept. So it doesn't fit on my graph, but that's where it touches the y-axis. Let's see. It is never decreasing, but it was always increasing the entire time. Is it 1 to 1? Yes. All log and exponential functions are 1 to 1. Is it growth or decay? It was bigger than 1, so it's growth. As x goes to the left, it levels off at a horizontal asymptote at 1. As x goes to the right, it's going up forever, so it's going to infinity. Okay. Let's repeat the process with number 3. For number 3, I'm going to rewrite that with the 5 at the end. So this is f of x equals negative e to the negative 0.17x, then with the plus 5. So I know it moved up 5. So 1, 2, 3, 4, 5. So here's my horizontal asymptote. Now, let's talk about what the parent function looked like. So I'm going to draw real lightly. E to the x would have been through the point 0, 1, and then starts off flat with the horizontal asymptote at 0, and then goes up forever. That's exponential growth. So E would have been exponential growth. However, this one is reflected horizontally. And so the negative out front just tells you whether it's an upside down or right side up exponential growth. So this is it's flipped upside down of exponential growth, but then we're reflecting it over the x-axis. So that turns it horizontally. So it's actually going to be decay. It's a flipped upside down, and it has to go through that 0.01. It's going to be like this now. And it also has a horizontal stretch. This is smaller than 1, so that's a horizontal stretch. And you find the amount that's, so I'm going to say HS for horizontal stretch of 1 over 1/17. It moved up 5. Would have been growth, but was reflected over both the y-axis and the x-axis. And it's in behavior. So as x goes to the left, negative infinity, f of x is going down forever. So f of x is going to negative infinity. As x goes to the right forever, this graph levels off at our horizontal asymptote, which is up 5. So reflecting upside down doesn't change growth and decay. It just flips it. It's still, you look at it, what would have been right side up is a growth or decay. But flipping it horizontally does reflect, or does change the growth and decay. So there is number 3. So let's talk about number 4. So number 4 is a natural log graph. So let's compare it to the original natural log graph. So the original natural log graph went through, and the vertical asymptote at 0 went to the 0.1 comma 0. So there's what it would have looked like with no transformations. So that's why I drew it real lightly in yellow, so we can barely see it. So this graph is going to have a vertical compression of 0.3. It moves right 1. It moves up 2. So the only thing I can show is the right 1. So I can go right, or there's my new vertical asymptote. And it would have had this x-intercept here, but it's got to go up 2. So here's my new, where it would have been the x-intercept. And then you can't really show the stretch or compression, so it can just draw kind of a rough sketch from here. So let's describe the in behavior. As x goes to the left, this graph doesn't exist. So the y value does not exist. But as x goes to the right, the function goes up forever. Now, describe the behavior near its vertical asymptote from the left and right. Well, the vertical asymptote was right 1. So as x goes to 1 from the left, it doesn't exist. So f of x does not exist. Nothing on the left side. F of x does not exist. As x goes to 1 from the right, the function goes, so we go to 1 from the right, it's going down forever. So we're going to negative infinity. And there's everything you need for the front side. So let's move on to the back side. So number 5, we have a log base 5, which is still basic. It's still a basic log graph. As long as that base of 5 is bigger than 1, it's still going to do what a normal log graph does. So that is, it has a 6. So I'd rather put a plus 6 at the far right end. So plus 6 here instead of at the front. Now, what do we know what's happening? I know it's reflected over the x-axis. It's reflected over the y-axis. So I'm going to say reflected over both. Reflected over x and y-axis. Axes. I know it's going to move up 6. Let's go ahead and do that part while I'm looking at it. I know there's a vertical stretch of 3. Vertical stretch, VS for short because I'm lazy. Vertical stretch of 3. There is a horizontal compression, because that's bigger than 1, so don't worry about the negative. The negative is the reflection. The 2 means a horizontal compression of, if you take the reciprocal of that, so 1/2. Now, the left or right movement, we have to take 1 divided by that negative 2. 1 divided by negative 2 is negative 1/2, which means right 1/2. And did I miss anything? So we had 1, 2, 3, 4, 5. 1, 2. Okay, we have all our traits. So the domain for a log graph only exists after the vertical asymptote, and our vertical asymptote moved right 1/2. So it's going to be, oh, but it's reflected. If it hadn't been reflected, we would have said 1/2 to infinity. But because this reflects over the y-axis, instead of going this way, it's now going to go this way. So it's on the left side of the horizontal asymptote, the vertical asymptote. So it's negative infinity until 1/2, and it doesn't touch the vertical asymptote. What is the range? Well, it goes down forever and up forever and everything in between, so all real numbers. Number 6, okay, we have an exponential function. It's exponential growth because the 4 is bigger than 1. It has a down 5. I see that one at the end, so let's get that one out of the way. Down 5. And I notice it has a negative 3 and a negative x. So the negative x means it's a it's reflected over the y-axis, reflected horizontally. And then the minus 3, but it's a negative 3 divided by negative 1 is a positive 3, so that means left 3. So if I think of exponential growth, remember exponential growth would have looked like this, but we're reflecting it over the y-axis, so it's going to look like this instead. So ignore that other line. And it went left 3. Well, that's not going to matter. That just moves this what would have been our y-intercept. So the domain is left forever and right forever. The domain's still all real numbers. The range, because we moved down 5, the range is 5 to infinity. And, down 5 would be negative 5. Sorry, almost missed that. I'm double checking myself with the key. Okay, let's look at number 7. Find a and b so that it satisfies the given condition. So we know we're dealing with an exponential function because it's a times b to the x. So a is like your vertical stretch. B is the number being raised to a power. So I know what makes, I'm going to clear the screen off for a second so I can see some things here better without my scribble. If I plug in 0 right there, anything to the 0 power that's a non-zero number is just 1. So that's a times 1 when I plug in 0. So that tells me it has to equal, whenever you plug in 0 for x, y is 10. So that tells me a is 10. So I know my function so far, just from plugging from the y-intercept, that f of x is 10 times b to the x. I just don't know what b is yet. And that's where when you plug in 1, plug in the other point, when x is 1, y is e. So here's my y. So 10 times b to the 1. So divide both sides by 10, and b is e divided by 10. So my function is f of x equals a, which we said was 10, times b, which is e divided by 10 to the x power. And there's our function. So this, if they ever give you the 0, they give you an initial value, they told you what a is. As long as x is 0, then we know a. So let's look at number 9. No, where's number 8? Okay, let's look at number 8, which is now number 9. So in a research experiment, a population of fruit flies was increasing according to the law of exponential growth. So we know it's an exponential growth problem. After 2 days, there were 100 flies. So I'm going to make a table, x and y. After 2 days, there were 100 flies. After 4 days, there were 300 flies. So we don't know a and b in this situation. But I do know that if I plug in 2 into this function, f of 2, that's going to give me a times b squared, and I know that equals 100. Okay, that didn't help me much. But I know if I plug in 4 from the second line here, a times b to the 4th is equal to 300. Well, now look, I have two equations that both have a's and b's in it. So if we take, it doesn't matter, the first equation, and let's solve for a. This would be a equals 100. If I would divide both sides by b squared, ignore this left side because that was when I'm telling you what I did. So if I take, I'm going to switch color so we can follow along here. So if I solve this one for a, you're going to divide both sides by b squared. So a is equal to 100 over b squared. Well, if we go substitute that in the other problem, if we make this a 100 over b squared times the rest of that problem, which the rest of that problem said times b to the 4th, and we knew it equaled 300. Well, b squared times b, that's 100b squared is equal to 300. Divide both sides by 100, and you get b squared is equal to 3. And then b would have to be the square root. Now, normally when we take a square root, we do positive and negative. But for exponential growth, we know we want a b that's only bigger than 1, so we only want the positive one. And now that we know what b is, we can find out what a is. Well, I want to take 100, that was 100, divided by b squared, so that's 100 divided by the square root of 3 squared. So a is 100 divided by the square root of 3 squared, which is 100 divided by 3. So my function, I'm going to write it here, even though that's the second, right here is where I'm pointing. So f of x is equal to 100 over 3 times b, which was square root of 3, raised to the power of x. Well, now, to get the answer to part b, all we need to do is find f of 5. So f of, that's supposed to be an arrow, f of 5, it's plugging in 5 into this, and I can't do that without a calculator, but it is just 100 over 3 times square root of 3 to the 5th. And if you use a, well, let me show you. Hold on, let me pull up a non-graphing calculator. So tools, math tools, we'll use this calculator right here. So we want, where is there a square root? So 3, I want the square root of 3. And is there a raised to, right? There's just a squared button on this one, so I don't like this calculator. So let me pull up a different calculator. So we wanted 100 divided by 3, and we wanted to do that times the square root of 3 raised to, now let's see, I can move it, doesn't matter, but the power inside or outside, raised to the power of 5. So let's backspace that out of there. Anyway, you get 519.6. And since we're talking about fruit flies, I would say that's 520 flies. Did it say fruit fly? Yeah, it did say. So 520 fruit flies. Okay, so let's continue. So I cleared the screen. So this is 520 fruit flies. I can't spell fruit flies. Whoops, I moved the screen by accident. I'm trying to adjust that back. Fruit flies. Okay, so F-I-L-E-S. F-R-U-I-E-T. Okay, moving on to number 10, which is technically, well, number 11, which is technically number 10. So we have a graph that's given, and we need to figure out what the parent function is. Well, it's exponential growth, I can see that, and I see it goes to the point 1 comma 10. If it goes over 1 and up 10, that's a 10 to the x. So this is, if you do that a times b to the x, we know when x is 0, you get 1, so a is 1. So it's 1 times 10 raised to the x. So this is just 10 to the x. This one doesn't have, the next one doesn't have that. So let's finish this one first. So on this one, we know the domain is still all real numbers. We know the range is above the horizontal asymptote, so above 0. There's a horizontal asymptote at y equals 0. The y-intercept is 0, 1. And it is, oops, I dropped my pen, it is increasing the entire time so that its domain existed, so negative infinity to positive infinity. Okay, on the next one, well, on this last one, I made a mistake, so I had to cut the video and had to fix my mistake. So I'm looking at number 11, part 2 here, this last one, and I tried to use the points A and B and tried to solve, but I completely forgot there's a vertical shift. If we look at this graph, this whole graph moves up too. So let me switch to them. So we have our function that's raised up 2. It's a times b to the x. But I know there's a vertical shift of 2 because it moved up 2. So can we figure out if we took away this shift just to see what this parent function, what this graph would look like? If we move this, if this was the x-axis now, this would be 0, 1, and that moves it down 2, so this would be 2, 9. Well, that's just 3 to the x. 1, if 3 to the x, if it's 2, 3 squared is 9, so it's just 3 to the x moved up 2. So I made this problem a whole lot harder by trying to plug in 1 and, or a is 1 and b is 2, and or whatever values they were, 2 and 11, and that did not account for the shift. So we had to do the vertical shift too. So we know the parent function was 3 to the x moved up 2. The domain is all real numbers. The range was everything above 2, so 2 to infinity. The asymptote had a horizontal asymptote at y equals 2. It touched the y-intercept at that point 0, 3. And it was increasing the entire time, so negative infinity to positive infinity. And so we didn't have to worry about an a because this one was just a 3 to the x, because 3 to the 0 is 1, 3 to the 2 is 9, but we just shifted that up 2, so that made this at 11 and this at 3. And that gave us our function, our transformation. So look for a transformation before you try doing the a to b to the x. And if it's going to be a transformation, there's usually not going to be an a if I had to guess on that kind of a problem. So that is everything you need for this lesson. Good luck to you.